Welcome to Rutgers Experimental Math Seminar. Today's speaker is Nure Kutlu from Amazon, who will speak about Okey and random combinatorial games. As usual, please mute yourself unless you have a question or comment. Thank you.
Hi everyone, I'm Nurai. I will be talking about Okey and random combinatorial games. I have two packages that I'll be going through sort of interactively. It'll be like an explanation of my work and a demo at the same time, so we can get started. Okay. So first I want to talk about the game of Okey because I'm pretty sure people are not very familiar with the game. So let's talk about that a little bit. It's a Turkish tile game. It's very similar to the game Rumikub, if you guys have played Rumikub. The tiles are the same as Rumikub. There are 106 tiles in the game, 104 numbered tiles. They're numbered 1 to 13, and they have 4 different colors with 2 copies of each tile. And there's also 2 jokers. So normally throughout the game, there's a process to pick a fake joker and replace it with the real jokers just to confuse the players. But for our sake, we're just going to use the 2 jokers that you can see here. And the game is played with 4 players. 1 player receives 15 tiles. The rest receive 14 completely at random. There's also a process to randomly distribute the tiles amongst the players in real life, but it doesn't really matter how you do it. It's random. So the way you play the game, the player with the 15 tiles begins playing. Every turn, the player that it's the turn of discards of a tile, puts it into a stack to their right, and the next player can either choose to take the tile, or if it doesn't suit their board, pick a random tile from the middle pile. And during each turn, a player's objective is to take a tile, either from the middle or from the previous player's discarded tile, and form runs or sets with their board. So a run is a sequence of 3 or more tiles in the same color, and a set is a set of 3 or more tiles of the same number and different colors. And if a player manages to put 14 tiles into runs or set on their turn, they can throw away the 15th tile in the middle and win the game. If they can't do that, they discard of 1 tile into the pile to their right, and the game continues. And a player has to have 14 tiles in runs or sets. They can't use that extra tile to create runs or sets. They need to discard of the 15th if it's on their turn. So this is the official way to play Okey, but we want to be able to generalize Okey for the sake of our experimentation. So let's generalize it. The generalized setup is you generalize the number of numbered tiles, number of colors, players, and how many tiles each player gets. So we can define the general tile deck in that way. That means the deck size is R times K, which R is the number of colored tiles, and K is the number of numbers in the tiles. So R times K times 2, plus, of course, the 2 jokers, which always stays the same. We call the number of players P and the number of tiles per player S. Generalizing Okey allows us to experiment with different types of game states, but the rules are always predefined because you can only transition from state to state with 1 different tile. So, sorry, 1 discarded tile and 1 new tile. Okay, so we can actually simulate generalized Okey. My package works to simulate generalized Okey. So in order to simulate it, you need a game state. So an initial state at first, which constantly changes throughout the simulation. And the initial state is a random dealing of tiles to P players, along with middle tiles, the current player or the current selected player, and any discarded tiles, which is initially discarded tiles. Technically, we don't really need to keep track of the discarded tile, but just the tile discarded by the previous player, right? And we also need functions to determine which tile to take or discard by that current player, which they can do this not randomly. They can take a look at their board and say, okay, I want this tile because it's going to help me make runs and sets, or they can pick from the middle randomly. And we need a function that determines whether a player can put all their tiles into runs and sets. So what if a player can put all their tiles into runs and sets, that means they win. And we need a function that determines which tile from the board to discard if they don't win. So the Maple package, Okey, has functions to initialize a game state, which takes in these 4 parameters that generalize Okey, and it randomly deals tiles. It finds runs and sets on the player's board and decides between picking a random tile or a newly discarded tile, determines winning states, and simulates an entire game of Okey. The simulation will give us the winning player along with the number of moves played, and if there are no middle tiles left, no winner, this is a tie. It'll just give us 0 in the return and the number of moves that took for it to tie. So we can actually do the simulation right now. Let me go to that. Okay, so let's do the verbose version first so we can see how the game is played. Basically, it'll give us the player's tiles. So this is obviously a generalized game that's much smaller, right? Than the original format. Actually, no, this is the original format, 13 and 4. Yeah. So this player has this grouping, which is these are all the tiles that are not grouped on their deck. And then each player has groupings, tiles, groupings and tiles, and then they just keep discarding of tiles, and at the end, they're leftover tiles, and then there are no middle tiles left. So playing this game, even slightly randomly, a lot of the times will result in a tie. And even with like smaller games, there are a lot of ties. I've personally tied in a game of Okey even when everybody's like fully using their brain. So this actually makes sense why there's so many ties. See, so in this game, it took 17 moves and player won. So let's go here. Okay, so that's the simulation.
So no,
and
in real life, it happens sometimes that there's a tie.
yeah, it does happen when there's a tie, but it's like less common for you to tie in real life because
use strategy. This is a random.
yes, yeah. I mean, there's still like very, very basic strategy in this, just to see if one tile will help form a set or a run or not. But it's mostly random, so that's why it's really difficult for the players to not tie. This simulation this simulate game T function can be used for like statistical analysis, but if I were to make this game simulation completely random, it's not very useful because nobody ever wins. It's always a tie. So yeah, okay, so there was another part to this Okey package. I'm not going to talk about the Okey package too much because I want to move on to the random combinatorial game package. But basically, we were analyzing games using game states and Markov chains. We wanted to model the game. Sorry if there's a lot of the siren is too loud, but hopefully it's not a problem. Okay. So we wanted to model Okey as a Markov chain, but we wanted to take the states in this case as a specific player's hand. So the function generate states creates all possible hands with R colors, K numbers, and S tiles on the board. As you can imagine, there's going to be a lot of states. And the function terminal states identifies winning states, so states where all of the tiles are grouped. And these become end states or absorbing states in the Markov chain. So, the reason why I have a state probabilities function is because actually every state does not have the same probability of appearing because some states will have multiple of the same tile, which does not happen uh, for other states. So for what I mean is like if you have the state or if you have the board with four tiles, they're all different, there's a higher probability that you can have that state than to have, let's say, a board with four tiles and the two tiles are the same, two tiles are the same, right? Because there's two of each tile. So this is actually kind of required for us to begin. We need to have a state probabilities vector, which is just the initial vector in the Markov chain. And then children states helps us see which states a certain state can transition to. So all the reachable next states. And the transition matrix basically is the probability that state I will turn into state J. And all the terminal states, instead of putting them as distinct states on the transition matrix, they're all collapsed into one absorbing end state. So everything has also a probability that they will transition to the end state. And then transition mul is a function that does the matrix multiplication. It basically tracks the winning probability, and each multiplication is like the next turn for that hand. So the unfortunate part about this is that there are a lot of states with Okey, a lot of transitions because it's a very complicated game, and it was taking forever to run this. So we took our experimentation over to random combinatorial games and tic-tac-toe, which I'll be moving over to. Okay, so what's a random combinatorial game? I mean, technically, the Okey game is also random, right? The initial state is random, the dealings are random, but what I mean by a random combinatorial game is that everything, including the rules, are random, the transitions are also random. So a random combinatorial game has n states numbered 1 to n, k players, which are all assigned a subset of states, random transitions defined between the states, and winning states for each player, which is a subset of all their states for each player. This is also random. So this function, randomCG, generates a random combinatorial game for n states and k players. It divides the n states, which are number 1 to n, equally among k players, and it picks one as an initial state. It generates random transitions between the states, generates win states as subsets of each player's states, and tie states, which are also a subset of the states, but a subset that is not in any of the player's win states. And the output for random CG is in the format initial state, win states, and the table of states and their transitions. This can be used later for simulating it. So I do want to demo that. Okay. We can take a look at this, but I don't really want to print the whole thing out because there's a lot. So the initial state is state 34 here. This is a table of winning states. So state 1 and state 23 are tie states. Player 1 wins if any of these states are reached, which 44, 2, 5, all of these states are also terminal states. And then player 2 wins, player 3 wins, and so on. And then this is the table that defines all the rules between the states. So everything that each state can transition to. Okay, and then we can also simulate it. I haven't gotten to the simulation slide yet, but I think it would be nice. So this is the verbose simulation for a game with 45 states, 4 players. As you can see, there's actually a lot, because it's random, there's a lot of terminal states that get generated. So it's very common for the game to end pretty quickly because, out of all of those states, somehow all of these states are terminal states. So player 1 is currently in state 29. That switches from 29 to player 1 in state 14. And then player 1 moves because state 14 is a winning state for player 1. So we can just keep doing this, but they're all different random games. Yeah, it seems like it doesn't take a lot for someone to win for this specific random combinatorial game. Okay, let's move on. Okay, so tic-tac-toe is not random. All the states are, predefined, and all the rules are also predefined, but we also did some experimentation on that. So I wanted to go over it. A generalized tic-tac-toe game is a K by K board where players aim to get K in a row. So this tic-tac-toe and this tic-tac-toe are different. This one also includes diagonals as in a row, but there's a function that generates a a tic-tac-toe game for a K by K board, and it has the same output format as random CG. So yeah, there's win states, tie states, and tie states are just fully filled boards that don't have K in a rows. So yeah, we can move on. Okay, so statistical analysis and game evolution. So this is the experimentation we did on the random combinatorial games. The simulate game, I already showed you guys the verbose version, but the terse version simulates a random combinatorial game and returns the winner and the game duration. So I think it would be, nice to try this with the terse version. Okay. See, so this one tied. Okay, this took more moves. This took 4 moves, and player 3 won. So this can be used for a lot of statistical analysis that we can do. The 2 statistical analysis functions I have are simustat duration and simustat win. Simustat duration runs simulate game t n times and returns the average as a polynomial, or the average duration as a polynomial. So duration sub I is the length of the ith simulated game, and the coefficient is the average frequency of games that lasted d many moves. Oops, oh, sorry. Okay. And simustat win runs simulate game t n times again and returns probabilities for each player's win outcomes, basically. So let's go ahead and simulate those as well. Oh yeah, also I have the simulate function for tic-tac-toe, but we don't need to do that. Let's go over duration. Okay, so these are the averages of, so this is how many times we ran it. 6 moves was 1 out of 100, 4 moves 1 out of 100, and so on. So it seems like it takes 1 move a lot more often for a random combinatorial game with 45 states and 4 players. And then we can do the simustat win, which is for the winning player. Okay, so 47% of the time it results in a tie, and then 24% player 1 wins, at least for this random combinatorial game. And we can find different statistics using the simulation function. Okay, so now let's move on to game evolution. Okay, So sometimes we want to be able to answer questions like, what's the probability that player 2 wins on move 5? For this, we can analyze the game evolution. So I have four functions for game evolution. Oper1 is just going to output a linear combination of states reachable from a specific state I, with let's try that. Oops. One. So we have this random combinatorial game. So initially, all of the states reachable from that state all have equal probability, right? So this is that linear combination. And then the oper function gives us a list where every element is the evolution. So basically, every element of oper is oper1 for that state. It is the evolution, so the linear combination of states reachable of each state. It's basically like the one-step evolution, and it's the transition operator. So we have all t sub i's, where t sub I is oper1 of gi, which is what we saw before. So let's try this. Okay. Let me actually label it so we can look at different parts of it. Okay, so T of 1 should be the same as oper1 of RG, 1, and X. I hope that makes sense so far. And then we have apply oper, which applies T to a linear combination F. If F is a linear combination of states in this form, then you substitute each X sub I by T sub I of X. So let's take one of the linear combinations, one of the linear combinations, and we can apply this operator on that linear combination using this function. Let's try that as well. Okay, so here we have this random combinatorial game. We have T, which is the operator. We have this initial linear combination, and we have the operated version of that. So X sub 9 is state 9, right? If we look at state 9, T of 9, it transitions to these states. So we should be able to see all of these in LC here, and we can see all of those. And then these could have the same states. They could add up and then, turn into these probabilities. Okay, and oops. We also have evolution game T. So this is basically repeatedly applying the operation. It returns a table of all probabilities that player I in T of I will win on a given turn n by applying the operator n many times repeatedly. So this is what helps us answer the question, what is the probability that player 2 wins on move 5, right? Let's try to demo that. I'm going to do the verbose version so it's easier to see what I'm talking about here. Okay, so the initial state is state 45. The probability that it ties on turn 1 is 4 out of 5. And, sorry. Okay, let me not go through all of them, but basically this is the verbose evolution here. And then lastly, there's the terse version, which just gives us the table over here. So these functions help us analyze the evolution of a random combinatorial game. There's also ones to analyze tic-tac-toe. Move on. Okay. Lastly, we can talk about generating functions. So we can use generating functions to do similar analysis of game evolution. Basically, I'm just using these evolution game functions to create these generating functions. Generating function duration returns this polynomial where the coefficient pi is a probability that the game ends exactly after I rounds. We can try that. So the probability that the game ends after one round is 26 out of 33, and so on. And then similarly, gen fun win. This is the generating function for the win evolution. So for a specific player R, returns a polynomial where the coefficient pi of x to the I is the probability that player R wins after exactly I moves. This gen fun win is for a specific player, so it's not, yeah. Okay, so for player 2, the probability that player 2 wins in one move is 2 out of 33, and so on. So these are the generating functions. And yeah, that's the end of my demo for my packages. Thank you all for listening, and thank you to Dr. Z. If there are any questions, I can take questions now.
Thank you for a very clear and insightful talk. We have plenty of time for questions. I have a question. So,
Yes.
did you try to compare the exact results that you get from the opera with a simulation? By the law of large numbers, if you run it many times, they should be close to each other. Have you tried that?
Yeah, I have tried that. So when I do like the simulation with like a lot of numbers, they're pretty similar. But when I try to do it one by one, there's some really random results from the simulation. But mostly it is similar, and I've compared it.
That's a good sign. Yeah, it's beautiful. You really have to write it up when you have a chance. Other questions?
Have you tried for the game of Okey to fix all of the parameters except one, and with perhaps relatively small numbers, and see what happens as you vary that parameter to see how the game behaves in terms of the parameter space of the game?
So I did try to do that, but with very small numbers in Okey, it just gives really results that don't really have any sort of pattern. Even when I vary one value, it's usually like it's hard to see a pattern when the game ends in one or two moves. So that didn't really help. And with larger numbers, doing statistical analysis was not really possible because it takes forever to run on Maple. So it wasn't too helpful, but I did do some with a small number of tiles, or sorry, a larger number of tiles, but a small number of tiles per player. And I believe that gave slightly interesting results, but it was again just like statistical analysis, so it wasn't anything too concrete, I would say.
And the tic-tac-toe for the 3x3 case, it's random play. You don't use any strategy, right? The whole idea is to do completely random moves.
Yeah, that's completely random moves, but the game rules and all the states are, not random.
Yeah. So do you know for random tic-tac-toe move, well, people don't use any strategy, just pick a random legal move. What's the expected duration?
Let's see. Oh,
I guess the upper bound is, I guess it's 9, right?
yeah. So actually with tic-tac-toe, when it was random, there was a lot of tying, but that was for the 3x3 case. But for the 2x2, it was ending fairly quickly. Like most of it was ending in like one or two two moves, obviously. But it was like a very small amount was actually tying for the 2x2.
But since tic-tac-toe is pretty small, the number of states is not that big.
Yeah.
So I guess you can, in principle, and probably also in practice, compute the average duration in a completely random game with a Markov chain. So it'd be interesting to compare it.
Yeah. Yeah, that's a good next step for this actually. I could try computing random combinatorial games and also for tic-tac-toe with Markov chains, but maybe for the random combinatorial games it would have to be with a smaller numbers.
Right.
Yeah.
Yeah, I guess very big, the
Yeah.
matrix. But tic-tac-toe, I think, is still feasible.
Yeah.
For 3x3 at least.
True. Yeah, so hopefully I can have a nice paper come out of this and record all my analyses there.
Yeah, that would be nice. So looking forward to it. More questions to Nore?
So have people looked at, I mean, the 3x3 case of tic-tac-toe when people don't play at random, they play to try to win is pretty, very well understood. And did you get any insight, let's say, into the 4x4 version of tic-tac-toe when people play non-randomly to win? Is there any insight into whether there are similarities as you increase the number of cells in the board?
Yeah, so I'm actually for the 4x4 case on Maple, it's having a very difficult time running. So I started to carry my code over to C++ so that I can actually run and test on the 4x4 or higher cases because right now even the 4x4 tic-tac-toe case, it'll freeze up. I can only run the simulation for it, which because if I try to run all the states or if I try to do analysis on all of the states, it's not working. But yeah, hopefully I can get some insight on that once I carry my package over to C++ and try experimenting on that.
Yeah, but I think what Joy is saying, maybe it's a little bit different direction. Try to build in some strategy and see what's going on. So that's also very interesting.
Yeah, I could try to build in some maybe controlled strategy into both the random games and the tic-tac-toe. I mean, the random game wouldn't be very easy to strategize, but for tic-tac-toe, yeah, I could try to do that to gain insight on how it works with strategy.
So as you know, for the 3x3 game, if the first player plays optimally, the first player can't lose, and it would be of interest. I mean, it would perhaps be of interest as you increase the number of cells in the tic-tac-toe board to know whether there are similar facts as to whether the first player can't lose or must lose or who knows. I mean,
right, yeah. Tic-tac-toe, yeah, you're right. So tic-tac-toe has been solved, right? So if you play it strategically with the 3x3, I guess that's like the first player is definitely going to win. But I don't know about the whole
you can't guarantee a win. You can guarantee
a tie. Yeah, a tie.
But the second player, no matter how well they play, if the first player plays optimally, the second player can't win.
Yeah. So yeah, I've never tried for the 4x4. So maybe that would be interesting to take a look at to see if the 4x4 has like similar results.
Yeah, it's a good project. It's not exactly random, but it's very interesting. More questions to Nore? Well, thanks so much for a very interesting, interactive talk. The recording will be available soon. We'll let you know. And please email me the slides for posting. Thanks so much for coming, everybody. See you next Thursday. Okay. Bye-bye. Aurora, please end this meeting. Bye-bye. Thank you, everybody.